Hello and welcome to this lecture on fundamentals of electric drives. In the last lecture, we were discussing about the DC chopper fed DC motor drive. We will see how we can achieve a dynamic braking using DC chopper. So, what we have here is the armature of the motor, which is represented by resistance, inductance and back EMF. And what we have here is we have a switch, a chopper switch, which is connected in parallel with the armature. And this is connected to a braking resistor, that is RB. So, this is our chopper switch. So, this is the transistor T, and we can define the voltage here, there is the armature voltage VA, and we have the armature current, and this is the equivalent circuit of the armature of the DC motor. Which is separately excited. Now, what we assume is that the motor is rotating and driving a load. So, the motor has a lot of kinetic energy. So, if we want to brake it electrically, we can brake it regeneratively, which will require the DC source to absorb the energy of the motor. Now, if we do not have a DC source, we can absorb the energy, we can brake it dynamically, which means we can brake the motor by transferring the energy to a braking resistor. That is what is being achieved here. Now, what we have here is that the switch, and we have sufficient armature inductance to make the current almost ripple free. What we assume here, the armature inductance is sufficient to make the current IA ripple free. So, this current IA is almost ripple free, which is almost a DC current. Now, let us draw the waveforms here. So, what we will be drawing here is the following. The time is in the x axis, and the voltage, the armature voltage and the armature current are in the y axis. This is the origin. Now, when the switch is closed, when the switch is closed here, this switch is closed. When the switch is closed, the voltage VA is 0. So, the voltage is 0. So, we can show that by 0 line here, the voltage is 0, and when the switch is open, the transistor T is turned off, the voltage rises to some finite value. So, this is the voltage across the armature. So, this is VA. Now, what about the current? Now, when the switch is closed, the current will flow through the switch, the armature is being short circuited, and we have assumed here that the armature inductance is sufficient. Now, since the armature inductance is sufficient, the current will charge the armature inductance, the current will rise, because this is the back EMF is sufficient here. So, the back EMF will charge the armature inductance. So, the current through the armature will gradually rise, be exponentially, and then when the switch is open, the current will flow through the braking resistor. This is the braking resistor. Now, we have assumed that the current is ripple free. So, what we can say that this ripple is almost negligible. So, it will again slowly decrease, and if you assume that it is ripple free, it will be almost a DC current. So, this is the current through the armature. So, this is almost DC current if you ignore the ripple. So, there is some ripple here, but if the armature inductance is sufficient, this ripple can be neglected. Now, we have to find out what is the power dissipated in the braking resistor. Let us see what is the energy dissipated in the braking resistor. So, if we try to find out the energy expression, so the energy consumed in the resistor RB. So, this is En. So, what is this En? We can assume that this current Ia is almost ripple free. So, we can say that Ia is almost equal to capital Ia, it is a ripple free current. So, this is also almost equal to constant current if you ignore the ripple. So, we can say that the energy consumed in the resistor is equal to Ia square into Rb. The loss is Ia square into Rb, and this is present for what time? So, we can say that this is T on and this is capital T. So, the braking resistor will be seeing the current in the following fashion. Now, if we draw the current through the braking resistor, the braking resistor will only see the current during the off time of the switch. So, this is the current through the braking resistor, and this the ripple has been ignored. So, this is T on and this is capital T. So, the time for which the current is flowing in the braking resistor is T minus T on, this time, which is capital T minus T on. This is the energy, this is the time for which the braking resistor is supplied with the current. Now, if you want to find out the power dissipated in the braking resistor, we have divided by time period. So, the time period here is capital T, because this is a repetitive waveform, this repeats after some time, the same waveform repeats here. So, this is a periodic waveform. So, we have to find out the power over one cycle. So, the power P is equal to the energy by capital T, that is equal to I square R B T minus T on by capital T. Now, this can be simplified as I square R B into 1 minus delta, where delta is equal to T on by capital T is the duty cycle of the switch. So, delta is the duty cycle of the switch T. Now, what is the effective braking resistance seen by the motor? So, what we are achieving here, by varying delta, we are able to vary the braking power. Now, what we can do here? We can change this delta. This delta is variable. So, if you change this delta, the braking power can be changed. It means the motor can be braked by controlling the duty ratio or the duty cycle of the switch, that is T. So, the effective resistance, the braking resistance seen by the motor is a variable one. Although we have a fixed resistor, by using a chopper switch we are able to convert that into a variable resistor. So, the effective resistance seen by the motor is this power by I square, Ia square. So, the effective braking resistance effective braking resistance is equal to P by Ia square, that is equal to R B into 1 minus delta, and hence by varying the duty cycle of the switch we can change the braking resistance. So, this is how the motor can be braked dynamically. In many applications it is not possible to regeneratively brake the motor, but we have to brake it dynamically using a resistor. Now, electrical braking has a lot of advantage. Now, when we go for electrical braking, there is no wear and tear of the wheel, because it is being braked electrically, the motion of the wheel is arrested, there is no friction. So, that is one of the advantages of electrical braking. So, advantage of electrical braking are the following: whether it is regenerative braking or plugging or dynamic braking, the advantages are the following. Number 1, no wear and tear. Of wheel or tire, because the motion of the wheel is arrested electrically. So, there is no friction between the wheel and the road or the railway track. Now, what is the other advantage? Other advantage is the torque can be controlled smoothly. Torque control is better compared to mechanical braking. So, these are the few advantages of having electrical braking. Now, we have already discussed about converter fed DC drives and chopper fed DC drives. Now, these drives sometimes are operated in closed loop. What do we mean by closed loop? When we want to control the speed accurately, we have to have a speed feedback. Suppose say for example, in a textile mill, we want that the speed of a motor has to be at 900 RPM. So, to maintain the speed at a particular value, we have to have a speed feedback. So, that is called a closed loop speed control. So, we will be discussing about closed loop control of DC drives. Now, usually let us see the block diagram. What we have here, we have a reference speed, that is omega m star, and we have a summer, and we feed back the actual speed here. Then what we do here, we feed this to a speed controller. and then the speed controller outputs the current. This is a current limiter. And the output of the current limiter is the reference current of the motor. So, the reference armature current, we show it as I A star, that is plus, and we have a current controller as well. So, we feed back the armature current, and we have another controller here, that is the current controller. And then we have the firing circuit, and we have the converter, and then we have the motor. And the motor usually is mechanically coupled to the load. So, we have the load, which is a mechanical load here. Now, the motor current is sensed here. So, we have the current sensor, the current sensor senses the motor current, and this feeds back the motor current to control the current in the motor, and the converter obtain the power supply in this case. Now, we have an inner loop here. The inner loop is a current loop, and in the outer loop we have a speed loop. The speed of the motor is sensed. We have speed sensor, the speed sensor senses the mechanical speed of the motor, which is omega m, and the speed sensor feeds back the speed to the input side of the controller as a feedback speed. So, this is the closed loop block diagram of a DC drive. Now, sometimes the converters are unidirectional. So, if the converters are in one direction, so for example, we have a fully controlled converter, it can only supply current in one direction. So, the current limiter will only have positive current limit. So, this current limiter sometimes will have the nature which is in one direction. So, if the converter is capable of supplying current in one direction, this is current limiter. And if the converter is capable of supplying current in both the direction, say for example, a dual converter or a 4-quadrant chopper, the current limiter can have a positive value or the negative value. Let us see how the control is accomplished. Now, we have a reference speed here, and the reference speed is compared with the actual speed. Let us say that the actual speed is less than the reference speed. So, what we have here, we have a speed error. So, we have a speed error, and the speed error is delta omega m, and the speed error is fed to the speed controller, and speed controller is usually a PI controller. a proportional and integral controller, which integrates and amplifies the speed error, and to prevent the output reaching to a very high value, we have the current limiter. So, the current limiter limits the value of the current to a positive limit and also to a maximum negative limit. So, the current is well within the capability of the motor. A DC motor can take roughly approximately 3 times the rated value of the current for a short time. So, the current limit is sometimes 1.5 to 2 times of the rated value of the motor current. And then this IA star is a reference current, which is the output of the current limiter, and that is compared with the actual current by means of this feedback loop, by this current sensor, which senses the value of the actual current and it feeds back this current, and then what we have in this case is a current error delta IA. So, the current error is fed to a current controller, which is again a proportional and integral controller, and the output of that goes to the firing circuit as a control voltage, and the firing circuit generates the triggering signal for the thyristor converter or the chopper converter, which feeds the armature of the DC motor. So, we have the motor here. So, the armature of the DC motor is fed from the converter. So, the current limit is important because we do not want that the motor current should reach dangerously high value, which will damage the windings. Depending upon the capability of the motor, we can set the current limit. So, by having a inner current controller, we not only protect the motor, but also we control the torque effectively, because torque is a function of current. So, when we are controlling the current, we are also controlling the torque of the motor. So, if we compare this to PI controller, the current controller is usually a fast controller. So, the current controller is faster than the speed controller. The reason is the current controller controls the current, which is an electrical variable. So, when we are controlling an electrical variable, the controller has to be fast acting. On the other hand, the speed controller controls the speed, which is a mechanical variable. Mechanical variable can change slowly compared to an electrical variable. So, the speed controller is a slower controller and the current controller is faster compared to the speed controller. Now, this completes the closed loop control of DC drives. So, depending upon a converter and the drive, we can configure the closed loop control and design the speed controller and current controller. Now, let us discuss about induction motor drives. The induction motors are AC motors and they are called the workhorse of industry. Roughly about 60 to 70% of the electric drives are induction motor. They are so popular, they are found application in various sectors, starting from domestic appliances to industrial application. One can find induction motor almost in every application in one's life. So, the induction motor construction is quite simple. So, what we have here, we have a rotor and we have the stator. So, this is the rotor and this is the stator, and the rotor usually carries bars or winding, and we have this air gap between the stator and the rotor, and the stator carries the AC windings, and these are the stator conductors which are placed in the slots and usually when we say that we have a 3-phase induction motor, this stator will produce or is capable of taking 3 phases. So, the equivalent circuit of this motor can be drawn in per phase. So, when we talk about the motor, when we try to find out the speed and the torque, we have to draw the equivalent circuit, and the equivalent circuit is drawn for single phase, for per phase equivalent circuit. So, in this case what we have here, we have the armature, the stator resistance, the stator leakage reactance, the rotor leakage reactance, and then we have the rotor resistance. So, after all, the motor consists of resistance and reactances. So, what we have here is this, that we apply certain voltage, this is the per phase voltage. This resistance represents the stator resistance, which is R s. This is the stator leakage reactance, which is X s. This one is the stator, the rotor leakage reactance, which is X r prime, referred from the stator side, and this one is the rotor resistance, which is R r prime, referred from the stator side, and this one is the magnetizing reactance, which is X m, and the rotor resistance is divided by a parameter called slip. When the rotor rotates, the slip is produced. The slip is given by S is omega m s minus omega m by omega m s. What is omega m s? Omega m s is called the synchronous speed, and omega m is the rotor speed. So, the rotor rotates in a given direction. Let us say it is rotating in the clockwise direction at a speed of omega m, and the stator is producing, stator has got 3-phase windings. So, let us say we have the 3-phase winding in the stator. So, we have phase A, we have phase B, and we have phase C. So, the stator has got phase A, phase B, and phase C, and the stator produces a rotating magnetic field, and the rotating magnetic field rotates at a speed which is omega m s. So, this is omega m s. Omega m s is the speed of the rotating magnetic field. So, the rotor will try to catch up with the rotating magnetic field, because when there is a rotating magnetic field produced, rotor has got conductors, and the conductors are short circuited, and this short circuited conductor will have induced EMF, and the induced EMF will circulate the current, and this current will interact with the field to produce a torque. So, the rotor will try to rotate and will try to catch up with the rotating magnetic field, and the differential speed, which is omega m s minus omega m, gives finite value of slip. So, this is how we draw the equivalent circuit, and the equivalent circuit is used to derive the torque and the speed of the induction motor. We conclude for today's lecture. We will continue this induction motor drive in the next lecture.